Imagine materials that can bend light in ways nature never intended, leading to invisibility cloaks and super-resolution microscopes. That's the tantalizing promise of metamaterials, but understanding their intricate properties is a major challenge. Exploring this exotic world requires advanced techniques, and circular dichroism, CD, microspectroscopy is proving to be a game-changer. Metamaterials aren't your everyday materials. They are artificially engineered to possess properties that go far beyond what's naturally available. Think of it like this: ordinary materials behave based on their chemical composition. Change the elements, and you change how they interact with light, sound, or electricity. But metamaterials? They play by different rules. Instead of relying on the what, the chemical makeup, metamaterials are all about the how, specifically, the geometry and arrangement of their internal structures. Image credit, CRAIC Technologies. These structures, often arranged in repeating patterns at the nanoscale, incredibly tiny, dictate how the material interacts with electromagnetic waves, sound waves, or even mechanical stress. It's like designing a tiny obstacle course for light, forcing it to behave in unexpected ways. And this is the part most people miss. These structures are usually much smaller than the wavelength of the radiation they interact with. This size difference is key to unlocking those unusual properties like negative refractive indices, bending light backward, reverse Doppler shifts, sound behaving strangely, and, yes, even the potential for cloaking devices. Metamaterials can be constructed from a wide array of materials, including metals like gold, silver, and aluminum, as well as semiconductors, dielectrics, insulators, and polymers. What's truly remarkable is their ability to precisely tune their behavior, adjusting their response across the UV, visible, and infrared spectrum. This tunability makes them incredibly promising for a whole host of next-generation technologies. We are talking about ultra-compact optical components that could shrink devices dramatically, super-resolution imaging that allows us to see details previously invisible, radar evasion systems for enhanced security, and incredibly sensitive sensors for detecting even the faintest signals. The ongoing advancements in metamaterials research are constantly pushing the boundaries of material science and applied optics. Now, how do we actually see and understand the complex behavior of these materials, especially their chirality, handedness? That's where circular dichroism, CD, spectroscopy comes in. CD spectroscopy is a powerful analytical technique specifically designed to probe the chiroptical properties of molecules and materials. Chirality, in simple terms, refers to a molecule or structure that is non-superimposable on its mirror image, like your left and right hands. This handedness causes them to interact differently with left and right-handed circularly polarized light. In essence, CD spectroscopy measures the differential absorption, delta A, of left and right circularly polarized light as a function of wavelength. If a molecule or material is optically active, chiral, it will absorb one polarization more than the other. The resulting spectrum reveals crucial details about the molecule's conformation, shape, secondary structure, and electronic transitions. Therefore, CD spectroscopy is an effective tool for studying chiral and asymmetric systems at both the molecular and nanoscale levels in materials science and nanotechnology. Beyond its traditional role in studying biomolecules like proteins and nucleic acids, CD spectroscopy is now widely used to characterize chiral metamaterials, plasmonic nanostructures, structures that interact strongly with light, and other engineered optical materials exhibiting chirality. Because of their nanoscale geometry, these advanced materials often display a significant difference in absorption between left and right circularly polarized light. Image credit, CRAIC Technologies. But here's where it gets controversial. While CD spectroscopy is great, analyzing tiny areas of metamaterials requires even more precision. That's where CD microspectroscopy enters the picture. CD microspectroscopy combines the high spatial resolution of microscopy with the power of CD spectroscopy. An instrument like the 2030 PV Pro integrated with CD microspectroscopy provides spatially resolved insights into the chiroptical properties of metamaterials and metasurfaces, thin, two-dimensional metamaterials. Metamaterials frequently employ nanoscale or microscale chirogeometries, rather than molecular chirality, to create novel optical phenomena such as polarization rotation, circular birefringence, different refractive indices for different polarizations, and asymmetric transmission, transmitting light differently depending on its polarization. CD microspectroscopy allows scientists to precisely measure the differential absorption of left and right circularly polarized light at specific locations on a metamaterial sample. 3-micron solid gyrate using reflectance CD microspectroscopy. Image credit, CRAIC Technologies. CD microspectra of a 3M solid gyrate. Image credit, CRAIC Technologies. By mapping these polarization-dependent optical responses, researchers can visualize local variations in chirality, identify fabrication defects, and correlate geometric asymmetries with their optical performance. This information is absolutely critical for refining the design and manufacturing of chirometamaterials, plasmonic arrays, and dielectric metastructures. These materials are used for sophisticated optical functionalities such as polarization control, manipulating the direction of light, enantioselective sensing, detecting specific chiromolecules, and optical data encoding, storing information using light. In essence, CD microspectroscopy acts as a vital bridge connecting material design, nanofabrication, and performance evaluation. It empowers the optimization of next-generation metamaterials and photonic devices that harness controlled chirality for groundbreaking optical applications. CRAIC Technologies 2030 PV Pro UV Visible NIR Microspectrophotometer, https://www.microspectra.com/products/2030-microspectrophotometer, exemplifies these capabilities. Designed for precise spectral and imaging research, the 2030 PV Pro allows scientists to directly analyze the optical performance of microscopic features, yielding invaluable data for material development. Its ability to perform transmission, reflectance, and absorbance measurements within a single instrument streamlines research workflows and enhances repeatability. The 2030 PV Pro stands as a valuable asset for materials scientists, physicists, and optical engineers engaged in metamaterial and metasurface technologies, bridging the gap between nanoscale fabrication and macroscopic optical innovation, thereby accelerating the creation of novel engineered materials. Image credit, CRAIC Technologies. This information has been sourced, reviewed, and adapted from materials provided by CRAIC Technologies. For more information on this source, please visit CRAIC Technologies. https://www.microspectra.com. So, what do you think? Are metamaterials the key to unlocking a new era of optical technology? What other applications do you envision for these fascinating materials? And perhaps most importantly, do you believe the potential benefits outweigh the complexities and challenges associated with their development and manufacturing? Share your thoughts in the comments below.